And now we would move on with the poster spotlight talks. So we have 5 exciting spotlight talks before the poster presentation today at 4 p.m. So I would like to ask all poster spotlight presenters, maybe you could move up the room, maybe you could sit here in the front so we can have a quick changeover as well. So and please remember you have 3 minutes for your spotlight, please try to stay within time. So the first presenter will be Samir Ambekar from the TUM and Helmholtz Munich.
Hi, Samir this side, and thank you for the introduction. I'm here to present our work on model merging and how exactly we propose our 2 contributions. That is the first one, why exactly mean merging fails. Second, how our entropy-adaptive method mitigates it. To begin with, we use this problem setup where we have 3 models with us, model A, model B, model C, which were trained independently on different hospitals. Now, they do not share data with each other. They are trained independently. The goal is to now merge these models such that they're able to address a new hospital or a new clinical site at test time. The first noteworthy contribution over here is that mean merging, if we just use mean to merge these models, A, B, and C, it's not useful. Why? It's because, first of all, they are non-adaptive in nature. They are static because you only estimate the mean of the models and you compute one basic model and use it for the entire test set. It's not useful. Second, it's initialization misaligned. It's because you are fusing components that have been differently trained. For example, you have an encoder that was trained on ImageNet and a linear classifier that was trained from scratch. Now, because these 2 models are inherently lying on different loss landscapes, you assume that the linear mode connectivity principle holds true, and still you perform the merging with mean merging. That's why you end up with weights such as 0.33 that is uniformly distributed, and then you perform the mean merging. Well, as I stated, we are using same coefficients for every unseen batch. That's why it's not useful. To mitigate this, we propose entropy-adaptive merging, where for every batch, we use the model entropy or the data entropy, by which we are able to estimate the weights adaptively for every batch. And second, it's connectivity stratified. That is, we adhere to the linear mode connectivity principles such that the encoder, which was trained on ImageNet, and the classification head, which was trained from scratch, have their own coefficients. The key insight here is that encoder and the head have different initialization regimes. That's why you cannot use one weight for both of them. Next, we demonstrate our effectiveness on 5 medical and natural vision benchmarks. The key insight over here is that we are fully online and our method performs better than existing baselines. Here are the data sets. For brevity, I can only state these things. Moreover, to conclude our method, for clinical deployment, mean merging silently fails. And turns out that we even ignore why is it failing. So our method is, first of all, merging weights such that in an adaptive manner, it is computed on a per batch basis. There is no static offline solution. We are fully online, and we do not use any fine-tuning. As for the second part, we estimate the encoder and the linear classification weights separately. We do not have the same uniform weights. The last conclusion is that we are robust, and there is no fine-tuning required. If you are interested to know how exactly we are using entropy, then you can find me at the poster. I'm happy to talk to you all. Thank you.